The spontaneous activity that I talked about in a previous video causes a new problem. That new problem has a solution, signal averaging. The problem is that if our sensory neuron is producing an average of 5 action potentials per second, releasing neurotransmitter 5 times per second, that doesn't mean it will produce 5 action potentials in every second. In the first second, it might produce 5. But in the second second might be 3, third second might be 6, fourth might be 7, fifth might be 4. If we average all of those, we might wind up with 5. But that creates a problem. How can an animal tell that this one is just the random background caused by the NAV 1.5 voltage-gated sodium channels that happens to be a little higher than the average, and that this one just happens to be a little bit lower? How can it tell a real signal from these random variations? And the answer is signal averaging. I'm just going to draw these sensory neurons now in a simplified form. Let's imagine that we have 10 of them. Each of them is getting input, and they might be very close to each other on the skin, on the tongue, in the nose, in the eyes. Each of them has spontaneous activity that produces 5 action potentials per second on average. So when there's nothing happening, when there's no input, they're simply producing 5 action potentials per second. If all of them converge on one target, we'll call this an integration interneuron, and each of these is producing an average of 5, then our target interneuron will receive the neurotransmitter from 10 neurons times 5 action potentials per second. The advantage is that while some of the neurons may be having fewer action potentials per second and others more over any given time span, they'll likely average out. They'll likely balance each other, with some of the low ones balancing the high ones. And so here, what I've shown is something that would be just a little bit below 5 action potentials per second. Let's think about what happens when we get a signal. So let's say we get a signal. Maybe it's photons hitting a photoreceptor or touch opening stretch channels. But we have a signal that for each of these increases the inside by +1 or 2 millivolts. Now that means we're going to rise above the average of 5 action potentials to, let's just say, 6 action potentials per second. Now remember, we still have a background where some at any given moment would be producing more and less. Maybe our first one happens to be producing the average of 6 action potentials per second, and our second one is producing fewer. Our third one happens to be producing more. The next one is producing also a few more, and the next one is producing less. Notice the average has now gone to somewhere around 6, and now our target neuron gets the neurotransmitter from the equivalent of about 6 action potentials per second. With that increase, it may increase from 5 to now 6 action potentials per second. And the advantage of signal averaging, that even though each individual receptor is bouncing around all over the place, above and below the average used to be 5, now 6 with this input, the target interneuron gets the average, and it's going to be much closer to the true signal. There's a cost to signal averaging. You have to spend resources on all of these cells. But for animals that are large enough, the cost is repaid by much greater sensitivity to small changes. Animals like ourselves can afford to do a lot of signal averaging because we have many, many cells.